Hope you guys are doing good. It's been a long time since I've made a video, but I have a midterm coming up for my final physics class in undergrad on a solid state physics course. So I'm going to review by, again, making videos. So hopefully this will help someone if you guys just want to listen along. And you might notice from the top, I'm going to be starting from chapter 3. And we have a slightly different format since my old computer wasn't working. This is all I could get it to work. But okay, without further ado, let's do chapter 3, where, as you guys can see, you guys will have the textbook on the left side that I'll be going through, and then I'll be writing my kind of notes on the right side. So chapter 3 is going to start with, it's about crystal binding and elastic constants. We're going to start with basically kind of how the bond interactions work, starting with van der Waals, and then learn about cohesive energy, then get into ionic bonds, covalent bonds, and so forth. So, okay, without further ado, let's get into the crystals of inert gases. So, all right, so basically we have different kinds of bondings. Here we have argon, right? Argon, noble gas. It's going to have van der Waals interactions, right? Because all of its shells are filled. Sodium chloride, salt. It's going to have ionic bonds, and then sodium has metallic, and then diamond has covalent. So we'll get into what all these are, but yeah. So basically, what we care about in this chapter is basically how do crystals work? How do they stay together? How are they attached? Are they just tiny little springs on each atoms connected to others? Or is there something deeper going on? So we're going to learn about van der Waals forces, covalent bonds, and so forth. And we're also going to learn about a term called the cohesive energy. Cohesive energy, which put simply is defined as the energy that must be added to a crystal to separate its components into a neutral free atom at rest at infinite separation with the same electronic configuration. In other words, it's kind of like the gravitational potential thing. If I have two things right here, how much energy do I need to take this guy off to infinity where the potential is 0? Okay, so let's see. So if we look at inert gases have full valence shells. They form the simplest crystals. The electron distribution is very close to that of free atoms, and their properties at absolute 0 are summarized in table 4. So, table 4, that's very far down. Okay, so here we have kind of a table of the cohesive energies. Hopefully you guys can see my mouse. And what's interesting to note here is if you look at the noble gases, right, if we just look at EV per atom, because I think that's the easiest one to visualize, look how small the energies are for the noble gases versus like, I don't know, iron. Iron is a much higher one, right? And that's because the noble gases only deal with van der Waals interactions, which we'll get into momentarily. Melting points, similarly, right? Because melting points are going to be intrinsically linked to kind of the cohesive energy, right? Because melting points is like, how can you break the bonds? Or at what point can you break the bonds? They have much lower melting points, and that's why these guys are almost always gases when we see them. This is in Kelvin, by the way. Okay, and then going to have to tilt your head for this one. We'll learn about what the bulk moduli and compressibilities are later on, so let's not talk about that now. But okay, so properties of inert gases, which is extrapolated to 0 Kelvin and 0 pressure. Nice. Okay. All right, anyways. So basically, what holds an inert gas crystal together? So van der Waals. So let's start with van der Waals. So what is van der Waals? Van der Waals, I guess London interaction. London interaction. Okay. So let's consider two identical inert gas atoms at a separation r large in comparison to the radii of the atoms. So here are my two atoms, and they're separated by a distance r. Okay, and then they all have like their little r's, but you know, r is much, much bigger than little r. Okay, so the charge distributions of the atoms are rigid. Like you imagine, it's just like a spherical ball with a uniformly distributed charge, right? The electrostatic potential of a spherical blah, blah, would be canceled outside a neutral atom by the electrostatic potential of the charge on the nucleus. So you basically be getting like 0 E field. from each of them, right? However, then, right, if we bring them close together like this, they wouldn't actually bond together, right? Because both of their contributions add up to 0. But if we instead think about that these electron shells are changing over time, right? It's kind of like not really orbiting the nucleus, but we have that cloud, right? Probability cloud of electrons around. So we can consider two identical linear harmonic oscillators separated by r, looking something like this. I think it's minus and then it's plus. This is like the spring or whatever. And then we have another one over here, minus, plus. And here's our spring. You guys see we have kind of a dipole moment here, and these can kind of oscillate, right? So let me first grab the diagram for you guys right here, just so I can draw on it. Okay, I did it backwards, but the same thing, right? You see what I'm talking about? Okay. What we can do then is we can write the Hamiltonian of the system. So we know each nucleus has a charge, or oscillator has a charge of plus or minus E, right? 1.6 times 10 to the 19. So we can basically write the Hamiltonian for the system, which 1 over 2m p1 squared plus 1 over 2 some constant for the force constants x1 squared plus 1 over 2m momentum 2 squared plus force constant again x2 squared. Okay, we have our kind of kx squared over there. All right, and then we basically have, since they're uncoupled oscillators, we can assume a frequency of omega naught, and therefore C is equal to m omega naught squared. So this just looks like your general Hamiltonian for a linear harmonic oscillator. Okay, ionization energies, whatever, doesn't really matter. Okay, long story short, the total energy required to move the first two electrons is the sum of the first and second ionization potentials. So clearly, if we look at, just gonna have to tilt your head for this one. Look at argon again, it has a pretty high ionization energy this time, right? Because it has a full valence shell filled, so it's kind of hard to remove that away. It likes to be filled. It doesn't want its electrons to be moved. Okay. All right. So then we can write the Coulomb interaction as the Hamiltonian as H1. And the Coulomb interaction, right? Like KQQ over R, but we're doing it in CGS units. So we basically just get rid of the constants, saying they're all 1. So it's E squared over R, right, for this to this. Okay, then it's E squared over R plus X1 minus X2. So R plus X1 is this to this. Okay, and then we have minus, right, because you have a positive electron, a positive charge, a negative charge, so you have E times negative E, so minus E squared over R plus X1, and then minus E squared over R minus X2. R minus X2 is this distance right here, and then R plus X1 is these two right here. Okay, hopefully that all makes sense. And then what we can do is, in the approximation that X1, X2 is much, much less than R, we can expand to obtain in lowest order. Hamiltonian 1 is basically minus 2 E squared X1, X2 over R cubed. Okay. So then the total Hamiltonian has the form for H1 can be diagonalized. So we get XS is equal to 1 over root 2 X1 plus X2, and then A is equal to, is defined as, these are all defined, 1 over root 2 X1 minus X2 for the summation and the difference ones. And then if we solve for X1 and X2, we get kind of X1 is equal to 1 over root 2 XS plus XA, and then X2 is equal to 1 over root 2 XS minus XA. And A and S refer to the symmetric and anti-symmetric modes of motion. Given by symmetric, they add, anti-symmetric is the difference. So we have momentums, PS and PA, associated with the X, right? So we can say P1 is equal to 1 over root 2 of the symmetric plus the anti-symmetric momentum, PA, and then P2 is defined as 1 over root 2 symmetric minus the anti-symmetric. So then therefore we can write to the total Hamiltonian, right, H, which is equal to H0 plus, or H, not whatever, H1, is equal to 1 over 2m PS squared plus 1/2 C minus 2E squared over R cubed, remember from our approximation, or tail expansion, and then plus 1 over 2m PA squared plus 1/2 C plus 2E squared over R cubed XA squared. Okay. And then we can do the same thing we always do with Hamiltonians, find out what omega is. So omega is equal to square root C plus or minus 2E squared over R cubed. Oh crap. All divided by M, right? We just do that from, you basically just take, like it's 1/2 omega squared X, right? And you need to put the M in there, and then you're chilling. Like for, from, if you guys remember from, Jesus Christ, like your harmonic oscillator class, I forget what it's called. So we get the omega naught frequency, we can expand, so we get omega naught is equal to, which equals, we can take out omega naught, and then we get 1 plus or minus 1/2 2E squared over CR cubed minus 1/8, and then the same thing, 2E squared over CR cubed, but squared because it's an expansion, and we just keep going. Okay, so, all right. So the 0-point energy of the system is given by 1/2 h bar omega s plus omega a, so symmetric and anti-symmetric. Because the interaction, the sum is lowered from the uncoupled value 2 times 1/2 h bar omega naught by, so change in potential is 1/2 h bar, the delta of the change in the symmetric and the change in the anti-symmetric, which is negative h bar omega naught times 1/8 2e squared over cr cubed squared, just bringing this down, which is minus, I guess they leave a constant a over r6. The point is it goes by 1 over r6. Okay, so the attractive interaction varies as the -6th power of the separation of the two oscillators. And the point of all this, right, is to realize that the van der Waals interaction is very, very weak. So it's also known as the London interaction or the induced dipole-dipole interaction. And for inert crystals, like crystals of inert gases, and also many organic molecules from biology class or organic chemistry classes. So basically, it's a quantum effect in the sense that as the change in potential goes to 0, h bar goes to 0. So the 0-point energy of the system is lowered by the dipole-dipole coupling of equation 3. Equation 3 is the Hamiltonian, right? Because we have 2e squared minus whatever, x1, x2 over r cubed. So it goes to 0, right? As r goes to infinity. Okay, so the van der Waals interaction does not depend for its existence on any overlap of the charge densities of the two atoms. Okay, so the approximate value of the constant a and 9, this constant right here, for identical atoms is given by, so a is approximately h bar omega naught alpha squared, where h bar omega naught is the strongest optical absorption line and alpha is the electron polarizability, which we'll see in a much later chapter, which I don't know if I'll get to because chapter 15 seems very far away, but we'll see. Okay, so that's the attractive interaction, right? However, we also have, as two atoms are brought together, right, their charge distributions, right, electron clouds, whatever, gradually start to overlap, which changes the electrostatic energy of the system. When you get sufficiently close, the overlap energy is repulsive, right? Because imagine I have a little plus here and orbiting minus, a little plus here, orbiting minus. These two boys get too close together. They don't want to be that close together. And then these two guys are also repelling each other. Okay. And basically, a lot of this happens due to the Pauli exclusion principle, which from your quantum mechanics classes, right, basically tells us that you can't, like, fermions have to, they don't want to be in the same state, right? So, cannot have all their quantum numbers equal. So, when the charge distribution of two atoms overlap, there's a tendency for electrons from atom B to occupy in part states of atom A already occupied by the electrons of atom A and vice versa. Okay, so basically in the simplest case, right, we have a hydrogen and a hydrogen. One to spin up, one to spin down, and then we get the net effect, right? You can fill their valence shell kind of, or helium, right, has one spin up, one spin down. I guess fusion, yay. However, if you have two upspin hydrogens and they form together, you get one spin up and another spin up, but you get in a different shell, right? So then your total energy is much higher versus if you had the spin up and the spin down together. So, okay, nice. So the Pauli principle prevents multiple occupancy, right? Fermions can't share the same state. And electrons distributions with closed shells can overlap only if accompanied by the partial promotion of electrons to unoccupied high energy of the atoms. Basically what happened in figure B. It's figure 5, right? No, it's not. Okay. I guess this is figure 5. They just didn't label it. Oh. Okay. So we're not actually trying to evaluate the repulsive interaction from first principles. But we can get experimental data on the inert gases can be fitted well by an empirical repulsive potential of the form B over R to, does that say 12? I think that says 12, where B is a positive constant when used together with long-range attractive potential of the form 9. Equation 9 was R kind of R over 6. 0, yeah, okay. So, let's see. So, it's usual to write the total potential energy of the two atoms at a separation R as U of R for two atoms is equal to 4 epsilon, and then we have sigma over R to the 12 minus sigma over R to the 6, where this right here is what we calculated before with the A over R6, and this is our new to the 12th, R to the 12th. Okay. Where epsilon and sigma are the new parameters. So 4 epsilon sigma to the 6 is defined as A, and or we can define it 4 epsilon sigma to the 12 is defined as B. Okay, so the potential, this one right here, the Leonard-Jones potential, shows us, well, if we look at the this is figure 6, yeah. If you look at the force from it, by just taking, you know, force is negative du dr, we can basically do calculations. So we see that as you get super close, boom, the potential jumps up. So the atoms can't actually touch, right? And then as you get farther away, you go away from the minimum. So the minimum is some kind of little happy point, roughly over here. Okay, and if we look at table 4, values of epsilon and sigma are given. Table 4 was up here, I'm pretty sure. There you go. We had the values of epsilon and sigma. These are the parameters in the Leonard-Jones potential. And we see that as you go up in the periodic table of elements, we get a higher epsilon and a higher sigma. Okay, sigma is given in angstroms. Okay, so unit of length. Okay, so other empirical forms or others. Okay, whatever. All right, so now we can talk about equilibrium lattice constants. We always want to talk about equilibrium. So if we neglect the kinetic energy of the inert gas atoms, The cohesive energy of an inert gas crystal is given by summing the Lennard-Jones potential over all pairs of atoms in the crystal. Right, so Lennard-Jones potential tells us how two atoms add together. So if you want to find the total energy of the system, we just sum over all of them. So we can say the total potential energy is 1/2 n times 4 epsilon. N is the number of atoms. Sigma j, I guess prime, I don't know why they're putting a prime, but whatever. Sigma over Pij momentum r to the 12 minus sigma j prime sigma over Pij r6. Okay, where Pijr is the distance between reference atoms 1 or I and any other atom j, expressed in terms of the nearest neighbor distance r. The factor 1/2 we do because we don't want to count each pair of atoms twice, right? Because we can say 1 to 2, that's the same distance as 2 to 1. That's why we have the 1/2. Okay. The summations in 11 have been evaluated, and for FCC, we have j summing Pij to the negative 12 is interesting, 12.13188, and then for Pij to the negative 6, 14.45392. Okay, so I guess they did it for a unit cell, is my understanding. There are 12 nearest neighbor sites in the FCC structure, and we see that the series are rapidly converging and have values not far from 12. I agree. The nearest neighbors contribute most of the interaction energy of the inert gas crystals, and the corresponding sums for, I guess, HCP, hexagonal close packed, is really, really, really similar. Okay, nice. I guess because they have a similar packing factor, I think. All right. So if we take the total energy from 11, this equation right here, also this one right here, and we want to find equilibrium, right? So where the potential is at a minimum. So we want du tot over dr to be 0. So we find a minimum, or maximum, I guess, but we're going to find a minimum, equals negative to ne. So we're just taking the derivative, and we're just putting in the numbers. 12 times 12.13, 12 over r to the 13 minus 6 times 14.45. We're just taking this simple derivative. That's why we get the r over 7 and then the 6 down there. So what we find out then is r naught over sigma is equal to 1.09. And okay, the equilibrium value of r naught is given by requiring that the u naught. Okay, yeah. So we find the equivalent value for r, basically, and we find that it's the same for all elements within an FCC structure. So we want the ratio of the equilibrium distance and sigma to be 1.09. So for different elements and stuff, neon has 1.14, argon 1.11, krypton 1.10, xenon 1.09. And the agreement with 14 is remarkable. Oh, yeah, my bad. In other words, we're saying that for FCC, we should get this value of 1.09, and here we see that we basically do. What's happening, what I'm assuming is happening, so xenon is the furthest down on the periodic table of elements. So it's going to be, yeah, because we see a downward trend. So it has the most like pure only van der Waal interactions and the stuff we were talking about before. And that's why it's the closest in agreement. And as you get lower and lower, you can probably get some maybe other interactions that happen when you have less electrons. Okay, so oh, I guess can be okay. It even goes over it. Can be explained by 0-point quantum effect for the lighter atoms. Okay, nice. All right, now back to that concept we were talking about, cohesive energy. Cohesive energy, right? Which is kind of the energy to take one atom, like let's bond together and move it to infinity, basically. So we can take our potential energy total of R, which is 2n epsilon of 12.13 times sigma over R to the 12 minus 14.45. This is for FCC. Sigma over R to the 6. Okay, and then we know when R is equal to R naught, our equilibrium, we get 2.15 times 4n epsilon, like that. How do we get 2.15, right? Well, we know this ratio over here is 1.09 because we have sigma over r naught, right? Or I guess 1 over 1.019, sorry. Same thing though. This is the same for all inert gases. So the calculated cohesive energy when the atoms are at rest. So quantum mechanical corrections act to reduce the binding by 28, 10, and 6 and 4% of equation 16 for neon, argon, krypton, xenon. Perfect. So what we see, right, is quantum mechanical corrections reduce the binding a lot more for neon, and then as you get heavier and heavier and heavier, it reduces it less. Okay, nice. So the heavier the atom, the smaller the quantum of correction. Smaller the quantum correction, right? Quantum, small stuff. We can understand the origin of the quantum correction by consideration of a simple model in which an atom is confined by fixed boundaries. If the particle has the quantum wavelength lambda, where lambda is defined by the boundaries, and the particle has kinetic energy. Okay, so we have p squared over 2m is our kinetic energy, which is h over lambda squared divided by 2m. Using the de Broglie relationship, that p equals h over lambda. Okay, yeah, makes sense. For the connection between the momentum and the wavelength of the particle, on the model, the 0-point correction to the energy is inversely proportional to the mass. That makes sense, over 2m. So in the final calculated cohesive energies agree with the experimental values of table 4 within 1 to 7%. Nice. Okay, so one consequence of this quantum kinetic energy is that a crystal of the isotope neon 20 is observed to have a larger lattice constant than the crystal of neon 22. Right, so we have more neutrons in there, which make it heavier. So then it's gonna shrink the lattice constant, is what I'm understanding. Yeah, kinetic energy is reduced by expansion. So then the observed lattice constants are 4.46 and then 4.559. So as you get larger, you get a more densely packed. Okay, nice. So ionic crystals are made up of positive and negative. Okay, nice. So now we're going to transition into ionic crystals, which you might know as like ionic bonds, right? Like some of the strongest bonds we can have. So ionic crystals are made up of positive and negative ions, and the ionic bond between results from the electrostatic interaction, right? We have a positive and minus connected together. So two common crystal structures found for ionic crystals, the sodium chloride, so salt, and the cesium chloride structures were shown in chapter 1 earlier. Electron configuration of all ions of a simple ionic correspond to closed electron shells as in inert gas atoms. In other words, when we take like NaCl, this is like a plus, this is like 1 minus, so then they form together, right, to make like a full shell. So the single charge ions have configuration. So lithium is a 1s2, and fluoride is a 1s2s2 2p6. So it's a single minus, and then lithium is a single plus. Okay, nice. So we expect that the charge distributions on each ion in an ionic crystal have approximate spherical symmetry with some distortions near the region of contact with the neighboring atoms. And we can confirm this by X-ray studies of the electron distributions, figure 7. Okay, let's look at figure 7 for a second. So electron density distribution in the base plane of salt after X-ray studies by some dude. Okay, nice. So we see it's basically spherical, and then we get kind of like some distortions where the bonds are. Okay, cool. A quick estimate suggests that we are not misguided and look at the electrostatic energy. So the distance between a positive ion and the nearest negative ion in crystalline sodium chloride is 2.81 times 10 to the negative 8 centimeters. And the attractive Coulomb part of the potential energy of the two ions by themselves is 5.1 eV, just for doing kQq over r squared. So this value may be compared with the experimental values of 7.9 eV per molecular unit for the lattice energy of salt with respect to separated Na and Cl ions, chlorine. So we're going to calculate the energy more closely. So electrostatic or Madelung energy. So long-range interaction between ions with charge, right, is just the Q squared over R, Coulomb, right? Between ions of the same charge. So the ions arrange themselves in whatever crystal structure gives the strongest interaction compatible with the repulsive interaction at short distances between ion cores. So the repulsive interaction between ions with inert gas configurations are similar to those between inert gas atoms. So the van der Waals part of the attractive interaction ionic crystals basically makes a very small contribution to the cohesive energy in ionic crystals by order of 1 or 2%. So the main contribution is the ionic, is the electrostatic or the Madelung energy, right? Because like a plus and a minus is going to be a lot stronger than like the van der Waals interaction, right? As we saw earlier, we had a scale as like 1 over r to the 6, right? Okay, so electron affinity is positive for a stable negative ion. Okay, so basically if Uij is the interaction energy between ions I and J, we can define all the interactions involving a single ion I as the sum over J of Uij, where the summation includes ions except J not equal to I. Okay, so we suppose that Uij may be written as the sum of the central field repulsive potential of the form lambda e to the negative r over rho, where lambda and rho are empirical parameters, and a Coulomb potential of just q squared over r. So in CGS, where we just ignore constants, lambda e to the negative rij divided by rho plus or minus q squared over rij. So these are our two, this is like our total energy. So the plus sign is for like charges, and the minus sign is for unlike charges, right? Otherwise, because it's just QQ. Okay. Yeah, so they're just making a note that we're doing in the CGS units instead of SI units because we don't want to carry all those constants. Okay. So the repulsive term describes the fact that each ion resists overlap with the electron distribution of the neighboring ions. And we treat the strength of lambda and the range of rho as constants to be determined from observed values of the lattice constant and compressibility. So we have used the exponential form of the empirical repulsive potential rather than the r to the negative 12 form used for inert gases. And we do this because it gives us a better representation of the repulsive interaction. So for the ions, we do not have gas phase data available to permit the independent determination of lambda and rho. And we note that rho is a measure of the range of the repulsive interaction. So when r equals rho, the repulsive interaction is reduced to like e to the negative 1 at the value at r equals 0. So in the salt structure, the value of Ui does not depend on whether the reference ion is positive or negative. And then the sum in 17, this one right here, can be arranged to converge rapidly, so its value does not depend on the site of the reference ion on the crystal as long as it's not near the surface. So basically, after a certain point, right, you only need a certain amount of atoms before it doesn't change much. So you can kind of do it like if you have a big crystal like this, minus, plus, dot, dot, dot. If it like extends all the way out here, any one of these atoms will kind of give you a similar result, as long as it's not next to the surface. Okay. We neglect surface effects and write the total lattice energy of a crystal composed of n molecules, or 2n ions, as just multiplying the two. U total equals n ui, where we use n rather than 2n because we must count each pair of interactions only once. In other words, each bond only once. So this is what we're counting. We're counting the bonds, basically. It's convenient to gain... it's convenient again to introduce quantities such as Pij, such that Rij equals Pij big R, where R is the nearest neighbor separation in the crystal. So if we include the repulsive interaction only among nearest neighbors, we have, again in these units, I'm just going to screenshot this and talk over it. We have our exact same interaction over here, which is for nearest neighbors. We have this special one over here because we need to include this form right here. And then otherwise, if it's a bit farther away, we just default to the Coulomb. Okay. And then we basically get the total energy then is... sorry. NUI, which is Z lambda e to the negative r over p rho minus alpha q squared over r, where Z is the number of nearest neighbors of any ion, so depending on the structure. And then alpha is the Madelung constant. And yeah, okay. The value, blah, blah. Okay, so basically the value of the Madelung constant is very important for the theory of ionized crystals, and we're going to discuss how to calculate it next. So at the equilibrium separation, right? So you basically want to find du, again, total, divided by dr to find r naught, equals 0. We get n dui over dr is equal to negative n z lambda over rho e to the negative r divided by rho, just by taking the derivative, plus n alpha q squared over r squared is equal to 0. In other words, r naught squared e to the negative r naught over rho is equal to rho alpha q squared divided by z lambda. So basically this tells us that r naught depends on, obviously, rho and lambda of the repulsive interaction. So for standard units, you can change back to it by putting in the correct value for q squared, which is q squared divided by 4 pi epsilon naught. Okay, so then the total lattice energy of the crystal of 2n ions, or n molecules, may be written as U total equals negative n alpha q squared over r naught. Again, in CGS, 1 minus rho over r naught, or if you wanted to turn this into SI units, you just divide the factor in front divided by 4 pi epsilon naught. Okay, and then this term, n alpha q squared over r naught, right here, is the Madelung energy. And we're going to find that rho is of the order of 0.1 r naught, so that the repulsive interaction has a very short range, right? Because we're getting basically 1 minus 0.1, which is basically just the same thing, right? All right. So, okay. Lines of alternating signs, distance r between ions. Okay. So, now we want to evaluate this Madelung constant, right? Madelung, I spell it wrong, lung constant evaluation. Let me take a sip of my tea. Okay, so remember, it's alpha, and alpha is the sum over j of plus or minus pij. Okay. For 20 was this total energy, right? In order for this to be stable, right, we need this one right here to be negative. Well, I guess positive, so you subtract a positive, but you need to subtract a positive. So we basically need alpha to be positive. So if we take the reference ion as a negative charge, the plus sign will apply to positive ions and then minus signs to negative ions. Okay, so an equivalent definition is alpha over r is equal to, remember, because p is just r times x or whatever, so r, ji plus minus over rj, where rj is the distance of the jth ion from the reference ion, and r is the nearest neighbor distance. So the value given by, basically, if you look at this line, r, this is r right here, and then rij could be, could be this, 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 etc. Okay. So as an example, we compute the Madelung constant for the infinite line. So we're going to do it for this line right here. Jesus. So we get alpha over r is equal to 2 times 1 over r minus, so we alternate 1 over 2r plus 1 over 3r minus 1 over 4r plus 1 over 5r dot 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 dot, right? Or alpha is equal to 2, 1 minus 1/2. Well, this is like a sum, right? Plus 1/3 minus 1/4 plus, and you might think it looks familiar, and that's because we can expand the expansion of ln 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x fourth over 4 dot dot dot. And then we can make x 1, right? So we basically get alpha is equal to 2 ln 2, right? Boom. So that's for a 1D chain, right? Okay. And then blah blah blah. So energy per molecule of a potassium chloride crystal shows the Madelung, Coulomb, and repulsive contributions. Okay, great. Basically, 1D that wasn't too bad, right? We could kind of tell that series was just log, natural log. But in 3D, it gets a little bit more complicated. It's not possible to write down the successive terms by casual inspection. And basically, the series will not converge unless the successive terms in the series are arranged that the contributions from positive and negative terms nearly cancel. And here are some typical values of the actual Madelung constants for a couple things: sodium chloride, cesium chloride, and zinc blend cubic, I guess. Okay, so nice. All right, here's a table, I guess, of the properties of these alkali halide crystals with the salt structure, which is just like the normal cubic ionic structure, right? Okay. You see the nearest neighbor distance here. It's increasing as we go down, right? And as it increases, right, the repulsive energy also increases. So yeah, we see the lattice energy compared to free ions decreases. All right. So I think we'll talk about this in covalent. All right, that was the ionic case, right? How about the covalent case? So the covalent bond is the classical electron pair or homopolar bond of chemistry. Basically, if you took OChem, you'll know about it. It's a strong bond, and the bond between two carbon atoms in diamond with respect to separated neutral atoms is comparable with the bond strength in ionic crystals. So basically, covalent is nothing to scoff at. It's usually formed from two electrons, one from each atom participating in the bond, and the electrons forming the bond tend to be partly localized in the region between the two atoms joined by the bond. The spins of the two electrons in the bond are anti-parallel, right? So that means you can have them in the same state. Spin up and spin down. And the covalent bond has strong directional properties, figure 11. So if you look at figure 11, right, we see that we can kind of get a directionality between the two germanium atoms, right? We kind of see how we have these strong center stuff over here and then weaker away. Okay. So, all right. Thus carbon, silicon, and germanium have the diamond structure, right, with atoms joined to four nearest neighbors at tetrahedral angles, even though this arrangement gives a low filling space of 0.34, oh wow, of the available space, compared with 0.74 of the closed pack structure. The tetrahedral bond allows only four nearest neighbors, whereas a closed pack structure has 12. So we should not overemphasize the similarity of the bonding of carbon and silicon. Carbon gives biology, but silicon gives geology and semiconductor technology. Okay, they just have similar bondings, what they're trying to say. So then the binding of the molecular hydrogen is a simple example of a covalent bond, right? So H2. The strongest binding, figure 12, occurs when the spins of the two electrons are anti-parallel. This should make sense, right? Because then they're in the same state and they're in the lowest state possible, so equilibrium, right? And the binding depends on the relative spin rotation, not because there are strong magnetic dipole forces between the spins, but okay, yeah. Because the Pauli principle modifies the distribution of charge according to spin orientation. Basically, it's in the lowest possible potential because you're in the lowest energy state, right? So in this spin-dependent Coulomb energy is called the exchange interaction. So if you look here, right, we see we have the up-up has a much higher energy than the up-down. So we have the symmetric and then the anti-symmetric. I guess parallel stable state and then non-stable state. My bad. But anyways, And then the N is the classical calculation with free atom charge densities. And then A is if you have parallel, and S is anti-parallel, which I guess I said it backwards, but it's what we expect, right? It to stay in. Okay, so the Pauli principle gives a strong repulsive interaction between atoms with filled shells. If the shells are not filled, the electron overlap can be accommodated without excitation of electrons to high energy states, and the bond will be shorter. So let's compare the bond length 2 angstroms of Cl2 with the interatomic distance 3.76 of argon and solid argon. And we can compare the cohesive energies given in table 1 of Cl2 and argon. So before I go to table 1, let's keep reading this. It's 5 electrons in 3p shell, and argon atom has 6 fill in the shell. So the repulsive interaction is stronger in argon than in chlorine. Okay, I guess we don't need to go there. We'll just take their word for it. All right, so the elements of carbon, silicon, and germanium lack 4 electrons with respect to filled shells, and thus these elements basically can have an interactive interaction associated with charge overlap. So basically, they're all lacking 4, right? So if they bond with themselves, they get a filled shell, right? They can form a tetrahedral system of covalent bonds, right? So imagine homeboy carbon over here. He needs 4 electrons. He shares with 1 carbon, shares with 1 carbon, shares with 1 carbon, shares with 1 carbon. And then that's just for like 2D. If you want to make it 3D, you have to make kind of the diamond structure, right? Because the diamond structure has 4 nearest neighbors. Okay, so basically to form a tetrahedral system of covalent bonds, the carbon atom must first be promoted to the electron configuration of 1s, 2s, 2p3. Thus, the promotion from ground state requires 4 eV, an amount more than regained when the bonds are formed. Okay, nice. So I guess we'll talk about this later probably. So this is a continuous range of crystals in the ionic and covalent limits. It's often important to estimate the extent of a given bond is ionic or covalent. So a semi-empirical theory of the fractional ionic. Okay, so they're saying a fractional ionic basically means how much of the bonds are like purely ionic versus covalent. And we see in silicon, it's purely covalent. Germanium, purely covalent. What do they change over here? Oh, because these are different crystals. Okay. And then as you start to kind of change their properties by bonding with not itself, like silicon and carbon, right? They have different like sizes, radii, and stuff like that. So you're going to get some ionic bonding there as well. It's basically as you make it less and less pure, you get more ionic bonds. Okay, so metals. We know metals. We love metals. Metals help us make our world run, right? Steel, Industrial Revolution, et cetera, et cetera. So metals are basically high electron conductivity, and a large number of electrons in metal are free to move about, usually 1 or 2 per atom. We get kind of a sea of electrons, to quote, like, I don't know, rudimentary physics. So the electrons that can move are called conduction electrons, and the valence electrons of the atom become the conduction electrons of the metal. So in some metals, the interaction of the ion cores, the conduction electrons, always make a large contribution to the binding energy, but the characteristic feature of metallic binding is the lowering of the energy of the valence electrons in the metal as compared to the free atom. So basically, when they can move around freely, you get a lower energy state, so it's more energetically favorable. So the binding energy of alkali metal crystals is considerably less than that of the alkali halide crystal, and the bond formed by a conduction electron is not very strong, so it's weaker, basically. The interatomic distances are also relatively large in alkali metals because the kinetic energy of the conduction electrons is lower at large interatomic distances, and this leads to weak binding. So basically, metals tend to crystallize in relatively close-packed structures, so HCP, FCC, BCC. This is why stuff like iron and all these other metals and stuff are FCC or BCC. So in some of these other closely related structures and not in loosely packed structures such as diamond. Okay. Basically, they need to be closer together so you can get those better conduction bands. So in the transition metals, there's an additional binding from inner electron shells. So transition metals and metals immediately follow them in the periodic table have large d electron shells and are characterized by high binding energy. Okay, nice. So the hydrogen difluoride ion is stabilized by a hydrogen bond. Okay, Probably should look at this one. Okay. So I guess next is hydrogen bonds. I guess I didn't really write anything for metals, but we're just talking empirically right now, I think. Okay, so because neutral hydrogen has only one electron, right, it should form a covalent bond with only one other atom, right? So we should be getting like H with H basically, or whatever else is like one free valence electron. That's a hydrogen bond. And it has a bond energy of 0.1 eV. So, oh, no. It's saying that this is what should happen, right? But the hydrogen bond is like, sometimes under certain conditions, a single atom of hydrogen is attracted by a rather strong force to two atoms, forming a hydrogen bond between them with a bond energy of the order of 0.1 eV. And it's believed that the hydrogen bond is largely ionic in character, being formed only between the most electronegative atoms, fluorine, oxygen, and nitrogen. Nitrogen? I think. Yeah, nitrogen. In the extreme ionic form of the hydrogen bond, the hydrogen atom loses its electron to another atom in the molecule, and the bare proton forms the hydrogen bond. So you basically have like H is just a single plus, and you have a minus boy over here, minus boy over here, and you get like that, I think. Okay. And then the atoms adjacent to the proton are so close. So they're super close. Oops. Like that. Thus, the hydrogen bond connects only two atoms. Figure 13. Let's make sure I'm drawing right stuff. We look at figure 13. Yeah. See, it just goes directly in the middle of the two. Okay, nice. The hydrogen bond is an important part of the interaction between water molecules and is responsible with the electrostatic interaction of the electric dipole moments for the striking physical properties of water and ice. How ice is less dense than water. It is important in certain ferroelectric crystals. Ooh, very cool. And in DNA. Okay, a lot of words, but I guess that's cool. So hydrogen can basically give up its electron and become like a chilling proton. Okay, so distances between, atomic radii. Atomic radii is important. I did briefly mention it earlier for reasons for metals. But basically, we can measure them very rapidly using XRD, X-ray diffraction, which is a characterization technique. Basically, you shoot X-rays at crystals and stuff, or you can do powder diffraction. And using Bragg's law and other stuff like that, you can reconstruct the spacing between atoms. So can we say that the observed distance between atoms may be assigned partly to atom A and partly to atom B? And can a definite meaning be assigned to the radius of an atom or an ion, irrespective of the nature and composition of the crystal? Okay, so basically we can't exactly say an atom is just a solid thing with a certain radius, right? Because the charge distribution around an atom is not like a sphere. It's not a perfect sphere that says, okay, all the electrons are chilling up to right here. Nonetheless, the concept of an atomic radius is fruitful in predicting the interatomic spacing. So we can model it kind of like this to kind of get how big each atom is. And then, like, for example, if we wanted to like make an FCC structure or something like that, you can have it like that. And then so forth. And you want to see like when they kind of touch, basically, how big they would be. And the existence and probable lattice constants of phases that have not yet been synthesized can be predicted from the additive properties of the atomic radii. So it's basically just a useful concept. So the electronic configuration of the constituent atoms often can be inferred by a comparison of measured and predicted values of the lattice constants. So to make predictions of lattice constants, it's convenient to assign, table 9, sets of self-consistent radii to various types of bonds. One set for ionic crystals, with the constituents ion 6 coordinated inert closed gas shell configurations, and another set for the ions in tetrahedrally coordinated structurals, and another set for 12 coordinated closed packed metals. So look at table 9. Radii for tetrahedral, radii for ions in 12 coordinated. Okay, so we basically see that like they have different values depending on how they're going to be oriented. Okay, which should make sense, right? Because then they have different bonds and so forth. All right. Oh, actually, and then we should see, right, for example, like, where's iron? Iron, right, only makes, like, FCC closed packed, so it gets 12 coordinated metals. We don't have, really, iron, for the other two. We see a lot of that for the metals, right? Versus like magnesium, right, can be all three. So I can have a bunch of different arrangements. Okay. So the predicted self-consistent radii of the cation sodium plus and the anion F minus, as given in table 9, would lead to 0.97 angstrom plus 1.36. You can just add them for the interatomic separation of the crystal NAF as compared to the observed 2.32. So basically, this R value is very useful because we can just add the two to basically get the net effect. Okay. Blah, 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 blah. So the interatomic distance between carbon atoms and diamond is 1.54 angstroms. 1/2 of this is 0.77 angstroms. And, okay. And silicon, which has the same crystal structure, 1/2. Oh, they're talking about, okay, that makes sense. So basically, we had a good agreement with the sodium fluoride at 2.32, and it's better if we assumed that they were neutral, which would lead to 2.58 from the other values in the table. And the latter value is 1/2 N distance in the metallic, interatomic distance in gaseous F2. So half the distance, basically, between the two. And for carbon, we get 0.77. And silicon, which has the same structure, 1/2 the interatomic distance is 1.17 angstroms. So, and silicon carbon, each atom is surrounded by 4 atoms of the opposite kind. So I have basically like a silicon here, and then I get 1 carbon, 1 carbon, 1 carbon, 1 carbon, and then each carbon is connected to 4 silicons, et cetera, et cetera, et cetera, et cetera. Right, so we have like, I don't know, Si, 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 and then I don't know, I think that might bond there, this might bond there, like that, something like that. But it's a 3D structure, so it's a bit more complicated. Okay. If we add the carbon and silicon radii just given, we predict 1.94 for the length of this bond, right? Which is in fair agreement with the 1.89 observed for the bond length. And this is the kind of agreement, so a few % off, that we'll be using for atomic radii. Okay, so ionic crystal radii for ionic bonds. That was for like the diamond structure atoms. Now, ionic crystal, right, is for the 6-fold coordination. So the ionic radii can be used in conjunction with table 10. So the interatomic distance D is represented by dN is equal to RC plus RA plus delta N, where RA and RC are the standard radii of the cation and anion, so like sodium and chloride. And delta N is a correction for coordination number. So if we look at the delta N for the different corrections for coordination numbers, we see how it varies. Nice. So let's consider barium, titanium, oxide, I guess? Is that an oxide? O3 is oxide? Yeah, I think it is. With a lattice constant of 4.004 angstroms at room temperature. So each barium 2+ ion has 12 nearest oxygen 2- ions. The coordination number is 12, and the correction of 12 applies, so 0.19. Okay. So if we suppose that the structure is determined by barium O contacts, oh, barium oxide, I'm dumb. We have, so D12, right, is 1.35 for the value for barium, 1.4 the value for oxygen, plus 0.9 the correction is 2.94 angstroms, or the last constant is 4.16 angstroms. If titanium oxide, I don't know, oxygen, contacts determines the structure, we have D6, so 0.68 plus 1.4, which equals 2.08, or alpha is 4.16. How do they get 2.94 to 4.16? Don't you add the delta? That is not making much sense. We have 1.35 plus 1.4 is 2.94. Then And shouldn't you double that? Huh. Interesting. Okay. Then I guess we get the actual lattice constant is somewhat smaller than the estimates and may perhaps suggest the bonding is not purely ionic, but partially covalent. So that's what the difference is between the estimated purely ionic case and then what happens in reality, since they're dealing with atoms of different sizes. Huh. Okay. Not too sure how they went from here to here. See, this one right here makes sense. You just double it, right? That's what they're talking about, the 1/2 n. But 2.94, or A is 4.16. We included the correction, so it should be fine. Maybe that was just for this? Huh. I guess probably they're telling us is that this is what we get expected. So we should be doubling this. And then this is what they actually got. So for barium oxide, it's actually a lot smaller than double 2.94. That's probably what it is. Okay, nice. All right, so the thing is, we can strain these materials, right? And we can kind of get view of like the elastic properties of material, like metal, right? You can bend certain metals. So we can do an analysis of elastic strain. So let's consider the elastic properties of a crystal viewed as a homogeneous continuous medium rather than as a periodic array of atoms. So the continuum approximation is usually valid for elastic waves of wavelengths lambda longer than 10 to the minus 6 centimeters, which means for frequencies below 10 to 11 or 10 to the 12 hertz. So some of the material below looks complicated because of the unavoidability multiplicity of the subscripts of the symbols, but basically basic physics principles are simple. We're going to use Hooke's law and Newton's second law, F equals ma. So Hooke's law, right, states that an elastic solid, the strain is directly proportional to the stress, right, negative kx. So the law applies to small strain onlys. We say that we're in the nonlinear region when the strains are so large the Hooke's law is no longer satisfied. So we specify the strain and the components of, all the directions, exx, eyy, ezz, exy, eyz, ezx, which are defined below. And we're going to treat infinitesimal strains only, so we shall not distinguish in our notation between isothermal, constant temperature, and adiabatic, constant entropy deformations. The small difference between isothermal and adiabatic are not really of importance at room temperature and below. So let's imagine that the three orthogonal vectors x, y, z of unit length are embedded securely in an unstrained solid as shown in figure 14. Boom, here are x, y, and z. They're just in a solid, chilling. And a uniform deformation, each primitive cell of the crystal is deformed in the same way. So we can basically write these new axes, x prime, y prime, z prime, using the strain values we found. So x prime, right, x prime moved this way. It's 1 plus the strain in the xx direction, plus the xy, and plus the xz for each of the varying components. And we just transform each of the axes to get the net effect of how it is. So you can imagine we have like a one atom here, 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 and then they moved here, here, and here. Okay, so the coefficients epsilon, alpha, beta define the deformation and are dimensionless and have values of much, much less than 1 if the strain is small. So in this case, this is obviously an exaggeration. But anyways, the original axes were of unit length and the new axes will not necessarily be of unit length. So if we did, x, y, z as actual unit vectors, x prime, y prime, and z prime are no longer unit vectors because when you dot it with itself, right, you get the 1 comes out and you get all these strain extra values, which, in the limit that these are all very small, it goes to 1, right? But okay, so therefore, x prime, right, is approximately 1 plus epsilon xx plus dot, 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 where the fractional changes of length x hat, y hat, and z hat are epsilon xx, epsilon yy, epsilon zz, right? Because we care about the first order right here, because when you square something small, it gets very small. Okay, so a lot of words, but anyways, what is the effect of the deformation? 26, so these basically like vector changes, on an atom originally at r equals xyz, right? So we have an atom that's chilling at this point, x given by x, y, and z, and the origin is taken at some other atom. So if the deformation is uniform, then after deformation, the point will be at the position r prime is x prime plus y prime plus z prime. This is obviously correct if we choose the x-axis such that r equals xx, then r prime equals x prime by the definition of x prime, right? We can just substitute the two. Okay. So the displacement r of the deformation we can define as just r prime minus r, right? That's just what you do. So if I have r vector over here, and then I have r prime like that, r prime like that, and then the difference is r, right? R prime. Okay. So that's going to be x prime minus x hat plus y prime minus y hat plus z prime minus z hat. Okay, so when we plug in our deformation stuff, we get r is equal to, I guess all the bolded ones should have arrows above them, but I'm lazy. So we get x strain in the xx plus y strain in the yx plus z strain in the zx, all for the x hat direction. So we're just plugging in what the difference in x prime is, right? Because if we go over here, we're subtracting away this 1 times the x thing because we're doing x prime minus x hat. So that goes away. And then I won't write the rest down. You can just see it here. I'll screenshot it to highlight it. But notice that there's no notice that it's just the strain components for each one, basically. Because the 1 plus epsilon xx, x hat direction, we're doing x prime minus x hat. So then the 1 goes away. And that's how we're just left with these components. Okay. We can write this in a more general form if we introduce u, v, and w, such that this right here gets simplified to r of r equals u r of x hat plus v r of y hat plus w r of z hat. If the deformation is non-uniform, we have to relate u, v, and w to local strains. So we take the origin of r to the close to the region of interest. Then comparison of 28. 28 is this one right here. And 29 right here. We can Taylor expand, right? We're assuming it's 0. We can say of r using r of 0 is 0, such that x in the epsilon xx direction is approximately x del u del x. And then same thing for y, epsilon yx is approximately y del u del y, etc. The partials for each individual one, right? Okay, so it is usual to work with coefficients EAB. I don't think that's a Greek letter. I think it's just E, rather than epsilon alpha beta, or alpha beta. We define the strain components simply as the partials for the relative directions, right? Where it's just the Taylor expansion of it, right? So the other strain components are defined in terms of the change in angle between the axes. So using 26. So we have, for the non-simple ones, for like EXY is defined as x prime dotted into y prime, which is approximately epsilon yx plus epsilon xy, which is just the partial of the two summed, right? So that's it. That's a U, that's a V. Okay? So hopefully that makes sense. So okay. Which basically a way you can kind of think about it is YX means you care about the X direction, right? But it was deformed, like your X-axis was deformed in the Y direction, so you take the partial of X with respect to Y. That's what it's du dy, because remember, u refers to x, v refers to y, w refers to z. So I guess I can screenshot these just because These are the actual relations. Very nice. And we can replace these kind of approximate signs by equal signs if we neglect terms of order strange squared, right? Because a small number squared is an even smaller number, so we don't care about it. So the 6 dimensionless coefficients are also related by the fact that E alpha beta is the same thing as E beta alpha, because it just relates the two directions, right? Okay, so dilation. What is dilation? It's gonna be a long video, I'm pretty sure. Sorry, let me get a little like stretching. I think we're doing pretty good. I think we're over halfway through it though. I hope. But okay, so dilation. So the fractional increase of a volume associated with a deformation is called dilation. So the dilation is negative for hydrostatic pressure. So the unit cube of edges x hat, y hat, z hat has a volume after deformation of, well, how do we find the volume of something? We take the dot product and cross it with a third, right? So v prime is x prime dotted y prime, normally put this in parentheses, cross z hat, right? That's the volume. So easiest way to do this, right, is you can rewrite this as just the determinant of x, y, and z above. So it's the determinant of x, y, z, like that, which, you know, if I write it out, is 1 plus xx, xy, xz, and then we have, I guess I just look, epsilon yx, 1 plus epsilon yy, epsilon yz, and then we have epsilon zx, epsilon zy, 1 plus zz, right? Yeah, nice. Like that. Which, if we take the dot, if we take the product rate, we can basically approximate it, right? Because we don't care about the square terms. So we basically get 1 plus e xx plus e yy plus e zz, right? Because the thing that matters, right, take the determinant of this, it's this cross with this, so we don't care about the square terms and so forth. So yeah, so we can get the dilation, delta, is defined as v prime minus v over v. So what is kind of the fractional difference between the two, which is approximately then the one just goes away, right? Because yeah, the if you take the volume, right, of something of unit 1 with unit 1, the volume is just equal to 1, right? Because it's, you're basically doing unit vector dot other unit vector, so it has a length of 1, cross other vector of length 1, so you get 1 again. Nice. Okay, so stress components. Stress components. So what I mean here, by the way, is just x hat dot y hat is like xy cosine theta. This is, you know, this will give you a 1. This is 1 times 1 times 1 is 1, and then 1 cross, you know, basically like 1 cross whatever it's called, 1 again. So 1 sine theta is just 1 times 1, which is 1. Okay. Anyways, stress components. So, right, we're dealing in 3 dimensions, so we're gonna have 9 stress components. In the x, y, z direction, then we have, I guess they do it weird. I guess they're doing it x in the x compression, x in the y direction, x in the z direction, and then you have this 3 times, right? Because you have y in the x direction, y in the y direction, and you have y in the z direction, then you have z in the x direction, z in the y direction, z in the z direction. So the capital letter indicates the direction of the force. So these are on the x, these are on the y, these are on the z. And then the subscript indicates the normal to the plane to which the force is applied. Nice. So in figure 15, we're basically showing all these things. So we have xx, xy, xz. So it's showing you which plane. So over here, right, we have the x in the x direction. Here we have the x in the y direction, and so forth. So for body and static equilibrium, yx has to equal xy, right? Because xy is the direction is x, and it's in the y, so then these two things have to equal each other right here. Like these two things have to equal but opposite in order to get the values, and same with these. Okay. So, and then the total torque is also 0 if yx equals xy. So if yx equals xy, right, and these two things cancel out and you don't rotate at all. So it doesn't rotate this way or this way. Okay. Where is this? The stress component xx represents a force applied in the x direction to a unit area of plane whose normal lies in the x direction. So here, the normal of x, right, is this plane that looks like this, and then the force in the x direction is this. So that's what xx means. So little thing means plane, big thing means axis, like direction of the force. Okay, so the number of independent stress components is reduced from 9 to 6 by applying to an elementary cube, as in figure 16, the condition that the angular acceleration must vanish. In other words, torque is 0, so alpha 0. So we get then that we get the component that yz equals zy, so just flip the two, and then zx equals xz, and then xy equals yx, because we're saying it's not going to be rotating. So stress components have the dimension of force per unit area or energy per unit volume. Force per unit area, F over A, that's like pressure. Oh, yes, it is pressure. So the strain components are ratios of lengths and are dimensionless. Nice. Okay. Wow, that's a lot of, I'm definitely not writing all this out, but I can screenshot it. So elastic compliance and stiffness constants. So Hooke's law states that for sufficiently small deformations, the strain is directly proportional to the stress. So the strain components are linear functions of the stress components. So we can write these out as shown, which I'm not going to do because it's a lot of writing, where our strain components, right, and stress components form a linear combination to get basically the EXX, EYY, and all that stuff. So we kind of see the relationship between these two, right, where the S and C are just the constants for the different ones. So the S11, S12 are the elastic compliance constants, and then the C11, C12 are the elastic stiffness constants, or from your engineering classes, the moduli of elasticity. So the S's have dimensions of area per force, volume per energy, and the C's have force per area. Okay, so pressure and I guess pressure to the -1. I don't know. What is the inverse of pressure? Out of curiosity. What is the inverse of pressure? Huh? That's not true. Okay, whatever. I guess P of -1. That's fine. Okay. So elastic energy density. So basically Hooke's law is just telling us we can make linear combinations of them, right? Because they're linear functions. All right, so elastic energy density. So 36 constants, so all of these, may be reduced in number by several considerations. So that's a lot of things to remember. So let's see what we can do to basically reduce them. So the elastic energy density U is a quadratic function, right? 1/2 kx squared for normal stuff, of the strains. In the approximation of Hooke's law, the energy for stretch springs, we can write U is equal to 1/2 sum over lambda equals 1 to the 6 sum over mu equals 1 to the 6. Why is there 6? Well, there's 6 strain considerations, right? Because we said that the torque has to be 0. C tilde lambda mu E lambda E mu, where the indices 1 through 6 are defined as XX, YY, ZZ, and then YZ, ZX, XY. And then the C's, tildes, are related to the C's of from before, below. So we'll see. The stress components are found from the derivative of U with respect to the associated strain component. This result follows from the definition of potential energy. So let's consider the stress X in the X direction of the X plane applied to one face of a unit cube, the opposite face being held at rest. This is equal to partial u del exx, which is defined as del u del e1, which is equal to c tilde 1 1 e1 plus 1/2 sum over beta equals 2, so the rest of them, to 6 of c1 beta plus c beta 1 e beta. And we note that the only combination of this stuff right here that enters the stress strain relations, so only these combinations enter it, where we have alpha and beta and then beta and then alpha. It follows that the elastic stiffness constants then have to be symmetrical, such that c of alpha beta has to equal 1/2 c tilde of alpha beta plus c of beta alpha, which is just c of beta alpha. In other words, that was a lot of fancy math to say that you can swap the indices. It's the same thing. So then therefore the 36 elastic stiffness constants are reduced to 21, right? Since we get rid of the ones that have different indices. Okay, nice. So elastic stiffness constants of cubic crystals. So the number of independent elastic stiffness constants is reduced further if the crystal possesses symmetry elements. Like always in physics, symmetry is always your friend. So it's a good thing that the universe likes symmetry. So we assert that the elastic energy density of a cubic crystal is U equals 1/2 C11. Then we have E XX squared plus E YY squared, so the strain in all directions, plus 1/2 C44 E squared YZ plus EZX squared plus EXY squared, plus C12 EYY EZZ plus EZZ EXX plus EXX EYY. Let's look at this for a second. So we're saying this first part makes sense. Second part, C44, so we have YZ, ZX, XY. Yeah, those are the components that stay. And then we have all possible permutations of the cross terms. So YY with ZZ, ZZ with XX, and XX with YY. And we're saying that no other quadratic terms occur such that XX and XY do not go, YZ and ZX do not go, and then XX and YZ do not go, etc., etc., etc. Okay, so the minimum symmetry requirement for a cubic structure is the existence of 4 threefold rotation axes. So the axes are in the 1, 1, 1 in the equivalent directions, figure 17. So the effect of a rotation of 2 pi over 3 about these 4 axes is to interchange the x and y according to these schemes. So yeah, when you rotate by 2 pi over 3, x goes to y, which goes to z, which goes to x again. So you basically get back to where you started from is the point. Okay, so under the first of these schemes, for example, we can say exx squared plus eyy squared plus ezz squared goes to eyy squared. Yeah, so you're just moving it around basically. Exx squared, which are 2 equivalent things, right? Similarly for all other terms in the 43 parentheses. So for these are the ones that work in terms of the rotation axes. So 43 is invariant under rotation considerations, but each of the terms in 44 right here is odd in one or more indices. So rotation in 45 can be found which all change the signs of the terms. So because EXY equals negative EX negative Y, for example, so 44 are not invariant under the required operation. So you'll basically be getting an extra negative sign. So these are our threefold rotation axes by 2 pi over 3. So we rotate it once, rotate it twice, rotate it 3 times. So you can imagine we take this point right here, rotate it once, I think it takes us to here, then it takes us to there, somewhere over there, and then it takes us back to here. So it's 1 rotate, 2 rotate, 3 rotate. And you can pick any corner point there and try it for yourself as well. Okay, so it remains to verify that the numerical factors in 43 are correct. 43 is this one right here. So probably C11, C44, and C12. So what we want to say then is we take the partial with respect to XX, which has to equal the force in the x direction on the x plane, or x face, I guess, which is C11 EXX plus C12 EYY plus EZZ from, you know, this fancy stuff over here. So we have this stuff right here. So we basically don't want to account for any of these because they don't work under the rotation axes. So we need to see if this is correct. So wait, why is it C12 times all that crap? Let me see. C12 EYY plus EZZ. Why is it like that? Okay. So the appearance of C11 EXX agrees with 38. Okay, that's what I meant. Okay, that's what I was just talking about. On further comparison, see, that's exactly what I was talking about, right? Because we get this C13 plus EZZ, and all of these need to remain, right? So that means C12 is equal to C13. So then we see that C14, which equals C15, which equals C16 have to equal 0 because we can't have those strain components, right, from symmetry. So then we basically then get is that C12 has to equal C13. So we just further reduced our amount of components. And then we want to check the 4-4 one. So we do partial del E xy is equal to x in the y direction. So C44 EXY. So we want to check C44. If we go up here, we find C44. C44 is over here. So that's the y in the z direction, right? Which is what we're saying here, right? Make sure I'm saying this right. Okay, does that say y in the x direction? What is that? Yeah, a y in the z direction is C44. Huh. And they're saying it's 43. 43 is this one right here. We want EYZ. EYZ, I agree. EZX, I agree. So all these are here in EXY. This is what we want. Okay. And then partial of xy is x and the y. X and the y. He has this one right here. Why is it 6 though? Maybe they messed up or I'm just tweaking. Oh, no. Okay, my bad. I just probably could have kept reading. Okay, so yeah, they do have x and the y. So we want this, right? But if we look, we see then for the x and the y direction, right, we get all these C6s, right? So that tells us then that this has to be 0, 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 this has to be 0. And this right here has to equal the C44 component. So then that's what that C61 equals C62, which equals C63, which equals C64, which equals C65, which all equals 0. And then C66 has to equal C44 from our earlier expression here. So then basically we can get an array of values for the elastic stiffness for a cubic crystal to this fancy dancy looking matrix where we see that a lot of the stuff gets zeroed out basically. If it lets me, there we go, it's screenshot. It's just extremely laggy because, oh, okay, I guess we'll wait. Probably pressed paste too many times, Jesus Christ. All right, whatever, I'll just leave it like that. But the point is, right, we get all the diagonal components stay. And we see that it's basically just all 3 of these are equal. All 3 of these are equal. So we have 2, and then we have all of these are equal, all of these are equal. So we basically have 3 components only. Okay. And then we get and that's just by repeating all the stuff. So for cubic crystals, the stiffness and compliance constants are related that C14 is equal to 1 over S44. C11 minus C12 is equal to S11 minus S12 inverse. So they have the inverse relationship, right? Because one's unit of pressure, inverse. So then C11 plus 2C12 is equal to S11 plus 2S12 to the minus 1. And these relations follow when we evaluate the inverse of this matrix over here. Okay, nice. Wow, this is going to be a very long video. I'm sorry. We don't, whatever. All right, that's what it takes to get through one chapter. So let's do it real quick. See how much more is left. Oh, we have all the wave stuff left. Oh, we're almost done. Nice, a couple pages left. All right, we're gonna get to the complicated stuff soon, though, unfortunately. But okay, so next topic is bulk modulus and compressibility. All right, nice. So let's consider the uniform dilation such that basically you have the same in each direction. EYY, EZZ, which equals 1/3 delta. Remember, delta is like V prime minus V over V, right? I think. Nice, I remember correctly. Perfect. All right. So basically they're all equal. So for this deformation, the energy density of the cubic crystal, right, is going to be given by 1/6 C11 plus 2C12 delta squared. So we can define the bulk modulus by the relation that U is equal to 1/2 bulk modulus delta squared, which is equivalent to the definition, right, from delta, that minus V dP dV, such that B is equal to 1/3 C11 plus 2C12. And then we can define the compressibility K such that K is equal to 1 over B. So values of B and K are given in table 3. We gotta scroll hella, don't we? Table 8, yeah, wow. Well, just look how far we've come. That's a good thing. Table 5, table 3. Here, I told you we'd go back to this, table 3. So out of curiosity, let's look at argon. I'm doing a lot of argon, so compressibility and bulk modulus, blah, blah. So argon, right, has compressibility of 79, which I think means it's pretty compressible, versus like, I don't know, it's like something that's like not compressible at all, like lithium, 8.62. Okay. Hopefully I don't have that backwards. But yeah, all right. Scroll all the way back. Wow, we did a lot of work today. That's good though. All right, nice. So, blah, blah, blah. Nice. Okay, now we can do elastic waves in cubic crystals, see how they kind of permeate or move. Elastic waves in cubic crystals. So we're going to do cubic, right? Because all that nice symmetry lets us do that matrix in equation 50 where it's, you know, it's a lot simpler, right? Imagine if we had a unique one for each direction. That would be terrible. Okay, so I'm considering, as in figures 18 and 19, these are figures 18 and 19, so we have a volume of a cube. Then imagine we have a bunch of springs. So the forces acting on elements of volume in the crystal, we obtain the equation of motion in the x direction as P partial U dt squared, which is dxx over dx plus dxy over dy plus dxz over dz, where again xx is this direction right here, I guess, like this direction, right, because it's the x plane, so normal to the x axis, but also and then in the x direction, and then we have all the other ones. All right, so here rho is the density, that's a rho, my bad. Obviously rho is density, mass over volume, and then we have u is the displacement in the x direction, and then right, the displacement in the x direction is given by the displacement in the x direction, x to the y direction, x to the z direction. Okay, so we have similar equations for the y and z direction. So out of curiosity, so then it'd be rho d squared, or del squared v, sorry, over del t squared is equal to del, it should be yx over del x plus del yy over del y plus del z, yz over del z, like that. That's what they mean. And then so forth for the z direction, which I won't rewrite. Okay, so it follows that then that this row, it's not a row, my bad, row of del squared u del t squared, so this equation right here, is going to be C11 del exx over del x, that's this component right here, plus C12, then we have del eyy over del x plus del ezz over del x. Remember, we're just rewriting our these equations right here from what we found, right? I guess you can also use the matrix form as well. So, right, xx is these things right here. Okay, and then we have plus C44 del exy over del y plus del zx over del z. Sorry about that. Okay, nice. So using the definitions, we basically get, I'm just going to screenshot this because I've been writing a lot. Hopefully that pastes within the next minute or so. Nice, it pasted. Excellent. Okay, I won't move it, it's fine. Okay, so then we get, he's just replugging in terms of u now, right? Like so. Okay, yeah. So we're just rewriting in terms of the definition for u, right, which was the x direction being changed. So the xx, xy, xz. Okay. So let's look at the figure now, just to kind of see what we're talking about. So we have a cube of volume, del x, del y, del z, acted on by a stress, negative xx in the x direction on the face of x, such that x is given x plus delta x is approximately that. It's approximately the same thing, plus the partial on the x face in the x direction times the displacement in the x direction. Okay. So the net force is given by using xx over del x, and the del x, del y, del z. Okay. So other forces in the x direction arrive from variation across the cube of the stress, which is not shown. Okay. So then the net x component of the force on the cube is Fx is del xx, del x plus del xy, del y plus del xz, del z. Well, remember, this is just all the forces in the x direction times the volume, like this, which should make sense. Okay, so the force equals the mass of the cube times the component of the acceleration in the x direction. So then the mass is rho del x, del y, del z, right? Because rho is m over v, so m equals rho v, and then this right here is the volume. Okay, and then the acceleration, right, is del squared u dt squared. So the corresponding equations of motions for the y and the x direction are found, again, by symmetry. Instead of having to redo all the math, right, we can just basically change the subscripts, and we get the exact same thing, except we change the u with the v, basically. So if we look at a, b, c, so we have a, all we did here is for the y direction, we changed these with v's, right? Let's check that. Check these with v's, and then we changed v to u, w to x, right? Or I guess to w stays a w for that. And then the same thing for the w direction or z direction. So now we want to look for simple special solutions to these equations, because these wave equations look kind of bad. So let's look for 57a, this one right here. One solution is given by a longitudinal wave, so u is equal to u naught e to the I kx minus omega t, where u is the x component of the particle displacement. So both the wave vector and the particle motion are along the x cube edge. So k is 2 pi over lambda, like usual, is the wave vector, and omega is 2 pi nu, I guess, which is the angular frequency. If we substitute 58 into 57, this is 58, and then 57a is this equation right here. We find that omega squared rho is equal to c11 k squared. Thus the velocity, right, velocity frequency over wave vector, omega over k, in the 1, 0, 0 direction is given by, vs is equal to nu lambda, which is omega over k, is c11 over rho to the 1/2. So if we consider a transverse or shear wave with the wave vector along the x cube edge and the particle displacement v in the y direction, such that v is equal to v naught e to the I kx minus omega t. If we substitute into now the b equations to the y direction, we get omega squared rho is equal to c44 k squared, right? Or we're just taking this from this expression here. Sorry, where is it? This expression here, because we're in the b direction now, right? And then we get the velocity. Similarly, it's going to look very similar as the first one, where the velocity is given by c44 over rho to the 1/2. Notice the similarities between these two. Okay, and then the identical velocities obtained at the particle displacement is the z direction. So thus, for a k parallel to the 1, 0, 0, the two independent shear waves have equal velocities. Now this is not true for k in a general direction of the crystal, just for the 1, 0, 0 direction. I'm getting tired of writing, so I'm just going to screenshot this page and talk about it so I can write over it. Ooh. All right, it's now in the 1, 1, 0 direction, which I guess I probably should have specified what these directions are. God damn it. This OneNote thing is huge now, this file, so it's kind of laggy, but whatever. Okay, so the 1, 1, 0 direction, right, is this direction. So if I have x, y, z, it's that direction. X, y, z. Okay, so propagating the face diagonal direction of a cubic crystal, so the 1, 1, 0 direction, because the elastic constants can be found simply from the 3 propagation velocities in this direction. So let's consider a shear wave that propagates in the xy plane. Okay, xy plane is this plane right here, with particle displacement w in the z direction, such that we have, so it's like, it goes like that, if that makes sense. Like in the plane, it's the displacement is in the z direction, right? So we have w is equal to w naught e to the I kxx plus kyy minus omega t. So then 32c, that's a long time ago. 32c is this expression right here. Zx is all that good stuff. Gives us omega squared. Oops, I need to scroll a bit more down. Okay, it gives us omega squared rho is c44 kx squared plus ky squared, which is just c44 k squared, independent of the propagation direction of the plane. So if we consider other waves that propagate in the xy plane with particle motion in the xy plane, we can let u equal u naught, same thing, and then v equal v naught. So this is y direction, this is x direction. And then from 57a and 57b, we get these expressions regardless, right? So this squared, this there, and then this right here for the u, which comes directly from this right here, right? We have the c11 and the c44 with both, and the c12 plus c44 with both, right? So c11 plus kx squared comes from this line right here, and then the c44 ky squared u comes from this line right here, right, because it's all v there, and then the c12 plus c44 comes from right here. Okay, and then the same thing for the y direction, so v. Nice. So then these pair of equations, right, has a particular simple solution for a wave in the 1, 1, 0 direction, for which kx equals ky. In other words, you have the same in both directions. So the condition for a solution is that the determinant, so if we want to find a solution for this, right, we need to make sure the determinant of this equals 0. And we can kind of immediately see this equals 0, right? Because it's this subtracted this minus this subtracted this. These two are equal. These two are obviously 0. These two multiplied together, right, is... so these two goes away, right? So then we basically get... God. I don't want to do this. Okay, whatever. So we have negative omega squared p plus 1/2 c11 plus c44 k squared minus this, so it's just w squared rho plus 1/2 c11 plus c44 k squared. So it just basically doubles, right? So then we get the roots of... Yeah, okay, yeah, that makes sense. So then we get the roots of... I'll just screenshot it, to be honest. We get these roots. Nice. So these are the values that have to, for the condition of it to be 0. And the first root, right, this one right here, describes a longitudinal wave. And the second root describes a shear wave. So how do we determine the direction of the particle displacement? Well, the first root, when substituted into 67, so right here, it gives us this expression right here. 1/2 c11 plus c12 plus 2c4 k2u has to equal 1/2 c11 plus c44 k2u plus 1/2 c12 c44 k2v. So when the displacement component satisfies u equals v, thus the particle displacement is along the 1, 1, 0 direction, right? Because if the x and the y component equal each other, then it's like that. And thus is parallel to the k vector. Then the second root, substitute the upper equation of 67 into here again, is going to give us the value of when u equals minus v. So the particle displacement is along the 1, minus 1, 0 direction. So like that, right? Yeah, like that. It is perpendicular to the k vector, right? Nice. That's correct. So selected values of the adiabatic elastic stiffness constants of cubic crystals at low temperature, blah, blah, given table 11. Okay, let's just look at these diagrams on the left over here. Wave in the 1, 0, 0 direction, we have C11 for longitudinal, transverse is C44. In the 1, 1, 0 direction, we have these kind of more complicated, slightly more complicated than what we just found before. Longitudinal was 1/2 C11 plus C12 plus 2C4, which we saw right here. And then the first transverse wave is given by C44, and the second one is given by this right here, C11 minus C12. Very nice. And then you also get waves the 1, 1, 1 direction as well. Slightly more complicated, but just 1/3 and then 1/3. Okay, nice. So we can look in table 11 that we're talking about here. Selected values of adiabatic elastic stiffness constants. And I guess for these crystals, we get these values for C11, C12, and C44. And we see how they change according to the cubic structure of it, or according to the elements. Okay, nice. So basically, these are the normal modes of wave motion in a crystal for a given magnitude and direction of wave vector k. So in general, the polarizations, the direction of particle displacement of these modes are not exactly parallel or perpendicular to k, but in the special propagation directions of 1, 0, 0, 1, 1, 1, and 1, 1, 0 of a cubic crystal, 2 of the 3 modes for a given k are such that the particle's motion is exactly transverse to k, and the third mode of motion is exactly longitudinal, parallel to k. So the analysis is much simpler in these special directions than in general directions, so that's why we did them. So, Jesus. Good work today. Let's quickly summarize what we just went over. So let me just screenshot these, and then I'll just briefly talk about it, because I know you guys are tired. I'm tired. So crystals of inert gas atoms, right? So argon, noble gases, blah, 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 stuff with their valence shells filled, are bound by the van der Waals interaction that we saw scales as 1 over r to the 6 from, expanding the Coulomb interaction and so forth. The repulsive interaction between atoms generally arises from the electrostatic repulsion of overlapping charge distributions, right? So you have a plus, minus like that, plus, minus like that. These get too close, we have that repulsion. Ionic crystals are bound by the electrostatic interaction, so plus to minuses. So you have like a plus and a minus like that. And the electrostatic energy of 2n ions of charge, so n molecules, or n bonds, sorry, is given by this kind of stuff with a Madelung constant. And R in the Madelung constant, right, is given to us basically depending on if it's FCC, BCC, HCP, whatever. Metals are bound by the reduction in the kinetic energy of the valence electrons, and in metals, as compared to the free atom, in a covalent bond is characterized by the overlap of charge distributions of anti-parallel electron spin, and then the Pauli contribution to the repulsion is reduced for anti-parallel spins, right, because then you're in a lower energy state, and thus makes it possible for a greater degree of overlap. And the overlapping electrons bind their associated ion cores by electrostatic attraction. Okay, that was a lot of words and a lot of good stuff, but hopefully you guys had learned something today. Sorry if I went super fast or if I got confused along the way. Tends to happen. But yeah, thank you guys for listening, and I might be making a video on chapter 2 and chapter 1 soon of Kittel's book of Introduction to Solid State Physics. So thanks for listening, guys, and I will see you guys in the next video.